Thank you, Mr. Chairman, for the presentation. My name is Luca Vecchiato, and I'm a research associate at the University of Padua in Italy. This work is in collaboration with my colleagues, Dr. Campagnolo and Professor Meneghetti from Padua, and colleague Jürgen Beer, Dr. Beer from Bundeswehr University in Munich, in Germany. This is just a preliminary result, so just a simple idea to detect the shape, the position, and the size of a crack propagating inside material. Can I go on now? Yes, thank you. So, applications are both in the field of fracture mechanics test, either structural and monitoring. As always, as we are involved in fatigue, we are interested in measuring the cracks propagating inside complex structure with complex patterns and shape. And for example, we have to say that we have to detect if a crack exists or not in the structures. Thereafter, we have to have some ideas about the shape, the location, and the size of these fatigue cracks. So we have to diagnose what are the geometrical features of these cracks. And finally, eventually, we have to provide some estimation of the residual life by performing some prognosis of the structural health condition of these structures. In this presentation, I will focus just on the diagnosis. So we want just to propose a new method for measuring crack propagating inside the material where we have no visual access to the crack front. When doing this, we have to deal with some required feature from the experimental technique we can use to perform such measurements. And in particular, such techniques must be for sure non-destructive. They should perform measurements in real time and locally in situ. They should have high resolution and many other properties, many other features. Again, we know there are a lot of different experimental techniques to measuring cracks, and this work wants to apply one method which has never been applied in the literature in such a way to measure crack propagating inside. So the potential drop method in a different way. So starting from this perspective, I want to spend just 1 minute on the potential drop method just to align everyone on this approach. It is that we have a specimen which has a crack inside, which is loaded with the fatigue loadings, and the potential drop consists of injecting a constant current through the specimens. And since the crack is propagating during the test, the resistance, the ligament section is reduced, and somehow the electrical resistance of the specimen is increased. And because of the electrical current is kept constant, we can measure the potential drop between points of the specimen itself, and we can relate, or better, we can measure an increase of the potential drop since Ohm's law is valid. So we keep constant the electrical current, the electrical resistance increase due to an increase of the crack length, and so we measure an increase of the potential drop. Thanks to some calibration curve, we can just translate the measured potential drop into a certain crack length. And this is how the potential drop method works. I'm pretty sure that many of you are familiar, and we know that this method is non-destructive in situ real time. So it is with it has a very high resolution and is quite widespread, and fracture mechanics tests are considered. On the other side, it has one main problem. When we apply the potential drop in its standard way, we're just using one single probe, so just measuring one potential drop on the specimen, we have just an idea on the size of the cracked area, so or the ligament section is the same. But we have the problem that we want to diagnose the size, the shape, and the position of a propagating crack. Let's take for this presentation just a simple example of a semi-elliptical crack propagating on a round specimen. And in this case, with just one single measurement of the potential drop, we can have the same potential drop for cracks having the same location but different shape, or the same shape but different location, or many other combination of shape, location, and size of this crack. So the idea was just measuring more than one point, more than one potential drop of the specimen surface, just to have an idea on how the potential drop is distributed on the specimen surface, and having more information, having more inputs, maybe we can just have more outputs about the crack geometry. So that is the idea behind all this work. Just limiting the problem for this application, for this case, just consider round bars subjected to mainly axial loading. So just to keep stuff simple, and just consider the case of one semi-elliptical crack propagating from the edge of the specimens. In this case, we have at least three unknowns, which are the angular position of the propagating crack, the crack depth A, and the shape of the crack described by the aspect ratio C over A. So these are our three unknowns. Thereafter, we have to choose the applied current, the magnitude of the applied current for applying potential drop. How many probes do we want to apply, or how many potential drop measurements we want to carry out on the specimens? And finally, for each potential drop measurement, we have to choose the position of two wires because we have to measure the potential difference. So we have two wires. So a lot of different variables to choose the axial and radial angular position of each wire of each probes in the specimen. So we have a lot of variables, even with this quite simple example. So how to do? The idea comes not a long time ago, and it all started assuming that for a moment we have known a certain database that for different bracket configuration. So let's assume we have for a certain bracket depth, length, position, and shape, and for a certain position of the probes and the wires of the probes, the corresponding potential drop. So we have a certain database that fulfill that sweep along many different configurations, all possible configurations in a certain way. And then add some more information that are how we have filtered, how we have configured and set up the potential drop measurements, and what are the measured potential drop on the experiment. Put the database information along with the measured potential drop in a certain algorithm, about which I will speak in a minute, and then perform some calculations to have an estimate of what are the crack depth, crack shape, and crack angular positions in this case. So the first question is, how can we create or have to have this initial database from which performing these estimations? And the idea was just using finite element simulations, wherein we can input into the analysis into the model the crack shape and potential drop setup parameters, performing finite element simulations to have the corresponding potential drop, and continuously update this database in a quite simple manner. This can take just a few hours to be done parametrically in ANSYS, for example. So the second point was, what kind of algorithm can we use to find what are the real bracket configuration beside my structures? And the idea is that we can use many different options, for example, machine learning, and this is something I'm working right now. But today I want to show you a quite simple idea that comes from the aerospace industry, which is based on an algorithm called probability-based diagnostic imaging. The idea is quite simple. So we have our database, the measured potential drop. We just add a certain uncertainty in the measurement, just because we have to deal with the real signal, measured signal. Then we just enter our database, searching for all configurations that have admissible potential drop. Let me explain another way. We enter in our database with the measured potential drop plus or minus the uncertainty, and we search for all bracket configuration we have in the database that fits with the values of the potential drop measurements. At the same time, we just we create a picture of the fractal surface. In this case, we have a planar crack, so it's just a 2D pictures. Otherwise, for 3D crack propagation, we can use voxels, so 3D model. Thereafter, for each configuration we have found, we create a new pictures where we highlight the pixels having the cracked area. So we will have many pictures highlighting the cracked area with a 1 value for the cracked area and a 0 value for the ligament sections. And finally, we can just add all the images together and eventually normalize it, identifying a certain region of the pictures that show to have the highest probability where the crack is located and what could be the most probable shape of this propagating crack. So just to validate this model, we performed some experimental tests, just performing some benchmarking to have a clear idea what is the real crack shape on the fractal surface, final fractal surface. And here you can see an example. At the same time, thanks to the fatigue testing, we have measured the potential drop, and for which market track front, we could measure the real experimental value of the potential drop. At the same time, we performed some finite element simulations and then entered the experimental value of the measured potential drop into our database and find all admissible configurations and generate for each one a corresponding picture, as I showed to you before. Finally, we merged all the images together and performed the final comparison with the experimental path and track chain. This exercise has been done in this case, considering round bars, notched round bars made of titanium 64, nothing special, any metals that is valid, just conductive material can be used. This is an example of finite element model and mesh, nothing special. What I want to show to you is that I performed some finite element simulations entering the crack depth and crack aspect ratio from 0.1 millimeter to 10 millimeter, and with this different aspect ratio. So nothing special, 2 hours finite element simulations, not so complex, quite simple to do it. This is an example of the experimental test, and this has been carried out on a shank hydraulic testing machines. Here, maybe you can't see the wires used to measure the potential drop since they are quite small, but they are copper wires of 0.1 millimeters. And we have chosen in this case, in this example, to adopt 4 different potential drops located at 90 degrees each one, and with the actual position of each wire symmetrically located with the crack plane on the notch tip, let's say. To benchmark the crack front height change, the applied load, so it has to keep almost constant the maximum K, and changing the load ratio to create different crack propagations or different roughness surface on the fracture surface, and then the possibility to measure finally the fracture surface image of the crack. Here, I'm going to show the results, and I'm almost done with the presentation. You can see on the bottom the fracture surface. We highlighted the benchmark crack front. The experimental crack front are highlighted for different crack depth by the red line, while the contour plot shows the estimate performed by our algorithm. You can see with the red, with the yellow color, the region where there is the highest probability of the test of the surface of being cracked somehow, and with blue, the region that has the lowest probability of being cracked. You can see that the higher, the longest the crack, the better the estimation is, while for quite small crack, for example, 0.1 millimeter, the initial notch, you can see that the algorithm is not so precise, so we can improve this method, but at least we can catch where that a crack exists, first of all, obviously, and then the crack, and that the crack is most probably located on the theta equal to 0 position. So somehow we have an idea that the crack exists, and we can do better using, for example, different techniques. So I'm done. I'm going to conclusions with this simple exercise, preliminary exercise. We have shown that we can use the potential drop in a different manner for measuring cracks inside material. And we have applied this exercise, this method, to single-edge simulated crack on round bars. And we have more ideas than time. We are actually improving this technique, just switching from the probability diagnostic imaging algorithm to machine learning, just to be more mathematically rigorous, let me say like this. But we want to work with multiple crack initiation, different crack geometry. We have many ideas about that, and for sure 3D problems of mixed mode crack propagations. With this, I'm done, and I'm able to for your questions, doubts, or criticism. Thank you very much.